Hello, welcome to Empowered Learning. This video is the third video in the Study of Spring Mass Systems series. So in the first two videos, we went over the theory behind modeling a basic spring mass system using a second order linear homogeneous equation where all of our coefficients are constant. We also considered the fact that our second order linear ODE could also be non-homogeneous, meaning that it doesn't equal zero. It actually equals to some non-zero value or function. And in the second video, we covered the concept of resonance and how that applied to the case one of the four different cases that we get for a spring mass system. And also in video number one, we talked about the four cases that result based upon the responses of the spring mass system in detail. If you are running into this video and you need a primer on those topics, then you want to find the part one and the part two portions of this video, same title, just part one and part two. If you're solely interested in learning how do I actually work spring mass system type problems, then this video, the part three and the part four that I will do will be the videos that you need to watch. And so in this particular video, I'm going to do out of the 6 examples I'm going to work examples 1 through 3, where the first example will just be me formulating my equation for my spring mass system and trying to decipher what will my equation look like when it has no external force being applied to the system, and what would it look like when it does have some kind of external force being applied to the system in general. So the second example, what we will do is consider the case where we have no external applied system on our spring mass system, or no external force applied to the mass in the spring mass system. Let me say it that way. And we're going to see what are our equations and corresponding responses, meaning our function y of t. What is that going to look like? And then we're going to look at graphs of all of those responses so that we can understand what the differences are in each of those responses. And again, if you watch the first video, the part one video, you'll see that what I was saying as far as what happens whenever we have a no dampening case versus an under dampening versus a critical dampening versus an over dampening case. We'll see all of those things sort of come to life in the graphs so that you'll know what it actually looks like when we have those types of responses. All right, so let's just go ahead and dive right into this first example here. So we want to suppose that we have some mass M for our spring mass system, and we suppose that it's moved such that the spring within our spring mass system is stretched 2 meters from its equilibrium position. Okay, and so what that's basically saying is right now our mass is at equilibrium. We're assuming that it's going to go out about 2 meters, and let's just assume that this is 2 meters. So where this point would be in our mass, that would actually be sitting about right here. So we're just imagining that we motor here has some force, we pull it out and we set it here, stretch out the spring here, of course, make this dash pod move, and it'll be right at the 2 meter mark. Okay. And we can do that with a 24 Newton force, so 24 kilogram meters per second squared type force. And after we do that, we take the mass and we return it back to its equilibrium position that you currently see it in. Okay. So essentially all we do is just say, hey, I'm going to push the mass out 2 meters. And I realize that it takes 24 newtons for me to be able to do that. And then I just slowly let the mass go back to equilibrium position, and that's it. And so what we want to do in this case, we want to use Hooke's law to find the spring constant, kappa, and the equation that represents the force of the spring due to it being stretched or compressed via that spring constant as well. Okay. And we know that if we do not stretch or compress the spring too much, it will follow Hooke's law. Now, if you watch the first video, then you kind of already know what the answer is going to be. But I'm going to quickly go through the derivation again, just for those of you that may not have seen that. So in short, we know that Hooke's law is just going to be force of a spring. It's just going to be F is equal to K times X. But since we're dealing in terms of Y here, let's go back. Since we're dealing in terms of Y here, we're going to label this Y instead of X. So let's go ahead and take care of that. So we're going to label this Y. And this is actually a difference in between a final and an initial, but the initial is always going to be at 0. So we just keep it like this. And we know that whatever force is being applied to the mass, the spring will have a force in the opposite direction. So that's going to be negative. And so this would be our equation for that. Now, what we need to do is find out what kappa is going to be. And since we have a force, and we also know how far we push the mass out, which is here, we can use that information to be able to come up with our spring constant. So here, our spring constant would essentially just be F divided by Y. And we're going to ignore the negative sign here just because that's just telling us the direction in which the force is in. So we're going to treat this as magnitude. And we know our force is 24 newtons. And of course, our distance that we pull the mass out is 2. And what that ends up being is 12. And this will be kg per second squared once we're done with that. And so for simplicity, we're just going to say that the force of the spring is just going to be a negative 12 watt. And so this would be what the actual equation for the force of the spring would be and what the spring constant will be. So now we'll move on to our second example. So what we want to do is state the equation of our what we call F resist, which is our force that's due to the air resistance and friction in terms of gamma, which is our dampening constant. And so here, what we had lumped into this in the part 1 video is we considered air resistance or air drag. We considered the surface friction. And we also considered the actual friction or resistance that comes from the fluid or material that's in the dashpot. Okay. And so the main thing is that all three of these, and assuming that the surface friction is going to be lumped in with the dashpot stuff, we're assuming that all three of these will be resistance based upon how fast the velocity moves. And so because of that, we simply said that F resist will just be minus the dampening constant times the velocity. And of course, velocity can be described as the derivative of position. So our F resist, or force that's based upon the dashpot and air drag and friction, is all going to be wrapped up into that. and it's just going to be negative gamma times derivative of y. So we have our spring force here represented in terms of y. We have our dash pod, air drag, and surface friction all lumped together being expressed in terms of y. So now that we recall that the total force in the spring mass system can be expressed as the force of the dash pod, air resistance, and surface friction all together as the F resist, the spring force and some external force has to equal F, where of course force F can be expressed as mass times acceleration due to Newton's law of motion, which we know acceleration is the second derivative of position. Okay, so knowing that and letting F other, which is going to be our external force, we're just going to call that F sub z for right now. We want to characterize or express this equation that's going to characterize the spring mass system. Okay, so from here we know that this is just going to be minus gamma y prime. We know for the spring this is going to be minus 12y, and for F this is going to be m times y double prime, because we know this is the Leibniz equivalent of saying the second derivative in prime notation. So if we have all of that, then essentially, again, we have this. I'll just rewrite it. And so here, if I add both of these first two terms to both sides, I will essentially have my double prime plus gamma y prime plus 12y, and that will equal to F sub z. Now notice that in our problem, our mass was 12 kilograms. So since our mass was 12 kilograms, we're going to replace the m that we had everywhere with the number 12. So that would be 12 here. We would have a 12 here, and we would have a 12 here. And so this would be our second order linear differential equation with constant coefficients that would let us know how to model our spring mass system. Now notice here that we have not given a value for the dampening constant or dampening coefficient, and that is on purpose. So the main thing that controls the different responses, given that your mass and your spring constant remains the same, is the dampening. So we need to see with our dash pod what type of material or fluid we're going to put into it to help dampen or decay the oscillations that the spring mass system could experience over time. And so depending upon how viscous the fluid or material that we put into the dash pod, that will determine the response that we get. And what we're going to see here in these next examples is what our equations look like when those values change. All right, so for our next example, we want to assume that our external force, which we called F sub z, is equal to 0. And then we want to know, well, what's the equation going to look like there? Well, we can just literally go back to our example here and just say, well, all this is going to be 0. Okay. And if that's the case, then we know that what this represents is an equation that's going to give us the homogeneous response of our spring mass system. And remember, In the part 2 video, we talked about the homogeneous response being the transient or impulse response, meaning that we have a quick burst of energy or force being applied to the system, then it goes away and it just kind of naturally does its thing. And depending upon how much dampening we have, that's going to control what that response is going to be like. Okay. And in all cases, except for the case where there's no dampening at all, our mass will eventually return back to equilibrium because of the fact that in all cases, except for case 1, when the dampening coefficient is 0, there will be some kind of decay component in it that will force the mass to basically settle down and approach y equals 0 as t approaches infinity. So for our example 2, what we now want to do is take the fact that we know that our mass is going to be 12 kilograms and the fact that our spring constant, we found that out, is also going to be 12 kilograms per second squared. And we're going to see what our spring mass responses, meaning our position functions, position function y of t will be for various values of gamma, or various values for this dampening coefficient. So the next set of examples, that is what we're going to look at. So in this example, we want to assume that we have no external force on the function, and we want to figure out, based upon different values of gamma or dampening coefficient, what would our responses be. So for example 1, or example A in this case, we want to find out what's going to be the general solution for the spring mass system if we decide to use no fluid in our dash plot, meaning we're basically saying there's going to be no dampening. And notice here that we have this chart that says, well, we're going to look at dampening in 4 different cases. When there's no dampening, dampening is 0, then when dampening is 18, then when it's 24, then when it's 26. And so these values have been strategically selected to showcase the 4 different cases for spring mass system responses, which is the no damp case, underdamped, critically damped, and overdamped case. So we're going to see what the response looks like when we have a case where there's no dampening whatsoever. Now, notice that our equation that we got from example 1 was 12 y double prime. And let's try to make that look a little bit nicer. So 12 y double prime plus dampening coefficient y prime plus 12y equals 0. Now, if our dampening coefficient is 0, then that means that this whole term is going to go away. And all I'm going to have left is the 12y equals 0. So we'll just get rid of all this here. Now, according to what we know about solving these second order linear homogeneous equations, where the coefficients are all constants, we know that we have a characteristic equation. And that characteristic equation, in this case, is just going to be 12r squared plus 12 equals 0. And of course, if we divide both sides by 12, we will essentially just get r squared plus 1 is equal to 0. And if we solve that, we'll get r squared is equal to minus 1. And of course, we know that that's going to end up with a purely imaginary solution here. And r just ends up being plus or minus square root of -1. Which r is plus or minus I, or 1i. So from this, we know that R is complex. And so there's going to be a real and imaginary part to it. And that's going to look like this. So that means that the real part, which is lambda, is 0. And the imaginary part is going to be 1. So let me write this and then we'll move forward here. So we know from what we know about solving second order linear homogeneous equations that this is a case 3 type situation for that body of knowledge. So our response will be y of t, and this is actually going to be the homogeneous solution because of the fact that our equation here equals 0. This will be e raised to the 0t times, pen kind of slid there. So it's going to be times constant times cosine of omega. And since omega is just 1, it'll just be cosine of t plus c2 sine of t. And of course, since e raised to the 0 is just equal to 1, we could really just get rid of that factor there. And just express our answer this way. So that'll just be c1 cosine of t plus c2 sine of t. And that would be our homogeneous solution for this case here. Now, next question says, will the dashpot slash surface of our spring mass system play a role in the dampening the position of our spring, of our mass M, if a force that's not equal to 0 was applied to the system? Okay, so I'll read that again. Will the dashpot and surface of our spring mass system play a role in dampening the position of our mass M if we have an external force that's not equal to 0 that was applied to the system? And the answer to that would be no. Okay, so we see from the math here that we have an oscillatory type system here, and it's just going to keep on oscillating back and forth forever and ever and ever. So the answer to that question would be no because of that. All right, so let's move on to the next example, or next portion of this example. All right, so now we want to find a general solution to the same spring mass system if we decide to use fluid A. And fluid A is just basically saying that we want the fluid with a dampening coefficient of 18. And so if we do that, then pretty much everything is going to be the same, except for now we're going to let our gamma here equal 18. So the original equation that we'll have will be 12y double prime plus 18y prime plus 12y, and that will equal 0. So this is what our equation would be in this case. Now, to solve this, of course, we have a characteristic equation again. And so now that characteristic equation will look like this. 12r squared plus 18r plus 12 is equal to 0. And so if I was to divide both sides of this equation here by 6, then I would have 2r squared plus 3r plus 2 equals 0. Now it turns out that in this case, we will not be able to factor out the left side of this characteristic equation by using traditional factoring methods for quadratic equations. So we'll use the quadratic formula to be able to come up with the roots. So we know that that would look like this if we did it. It would be a minus 3 plus or minus. Then, of course, that'll be 3 squared minus 4a, which is 2, and c, which is also 2. And all that will be divided by 2 times a, in this case, would be 2. And again, I'm just doing it via the quadratic formula. In actuality, the 3 here represents the place of what gamma would be. But of course, everything is being divided by 3. So this would be, gamma divided by 3, gamma divided by 3, 4 times mass divided by 3, and spring constant divided by 3, all over 2 times the mass divided by 3. Sorry, mass divided by 6. Yeah, so all those were divided by 6, not divided by 3. Anyway, so my point here is that once we work all this out, what we will end up with is 3 plus or minus, and in the under the radical, we would have 9 minus 16, which would give us a negative 7. And all that over 4. Let's make that look a little bit nicer. So all that over 4. And of course, this would end up being a negative 3 over 4 plus or minus square root of 7 over 4i. And thus, we see that our solutions are complex. They are not purely imaginary, but they are complex, which means we have a real part and an imaginary part. Okay. Now, going back to the previous example here, notice that our example here, our roots were purely imaginary, which means we had no real part, and thus we had nothing to, we had no exponential part to multiply this by. Okay. And that is what's going to keep our spring mass system from not decaying, or to keep the mass from not going back to equilibrium as t approaches infinity. The fact that we do have this real part, that is the thing that is going to help us to be able to eventually get the mass back to equilibrium as time approaches infinity here. So we got equals lambda plus or minus omega. And what that means is that our lambda here is going to be negative 3/4. I'm trying to get this pen to work with me here. And our omega now is going to be square root of 7 divided by 4. Okay. And notice here that if we were to calculate square root of 7 divided by 4, that would be a value about 0.6667, something close to that. But notice that it's less than 1, meaning it is less than the natural frequency of the system when we have no dampening. And so this is what I was talking about in the part 1 video when I said that the angular frequency for a case 2 type situation, which is the current example that we're working on, is always smaller than the angular frequency for a case 1 situation. So this is case 1, and the omega here, which is the square root of 7 divided by 4, which is about 0.66 something, that is basically, this is a case 2 situation. So our response looks the same in general, meaning that we would have e raised to the lambda t times c1 cosine of omega t plus c2 sine of omega t. And now our lambda is something that is non-zero, so we can actually write it in. And we have c1 cosine of square root of 7 divided by 4, all that times t, plus c2 sine of square root of 7 divided by 4, all that times t. And that would be our response. And remember again, it is this portion of our response that is making our mass eventually return back to equilibrium as time goes to infinity. So for example D in example 2, we want to find a general solution for the spring mass system whenever we use fluid B. And basically that means that our dampening coefficient is now going to be 24. And as you see, I've already written what the second order differential equation would look like when our dampening coefficient is 24. Now, of course, what that means here, since we can divide all terms by 12, that would just be y double prime plus 2y prime plus 1 equals 0. And that translates to a characteristic equation of r squared plus 2r plus 1 equals 0. And this would just be r plus 1 squared equals to 0, which means r plus 1 is equal to 0, which means r is equal to a negative 1. And this is the double root situation here. And so what that tells us is that in terms of second order linear homogeneous equation solving responses, we're going to have a case 2 type situation, which means that in general, we're going to have a C1 plus C2t times e raised to the RT. And of course, our R in this case is going to be a negative 1. So we can just replace R with a negative sign. And this is essentially our response. So lastly, we're going to look at what happens whenever we allow our dampening coefficient to be 26, okay? And before we do that, I just want to make sure that in terms of the cases here, this is the case 3, or critically damped situation, okay? I'll go back and label these. This example here was the case 2, and this is the underdamped situation, or underdamped case, meaning that there is some dampening, but not enough to make the mass go back to equilibrium fast. Of course, this situation that we have here is the case 1, which is no dampening whatsoever. And so because of that, our mass never returns back to equilibrium. So now for example E, what we want to do is use fluid C, which means that we want our dampening coefficient in this case to be 26. And of course, when we have that, we see that this is the resulting second order linear ODE. Again, if we were to divide all sides, well, all terms of both sides by, I think it's 2 here. Yeah, I want to do 2 because that'll make the numbers nice. Then our characteristic equation here would just end up being 6r squared 13r plus 6 equals 0. And this ends up factoring to 2r plus 3 times 3r plus 2, which is equal to 0. And from that, of course, if we set both 2r plus 3 equal to 0 or 3r plus 2 equal to 0, that would basically say that r is either equal to negative 3 over 2 or r is equal to negative 2 over 3. Now, notice here that both of our roots, we're going to call them R1, R2, are negative. And remember, for spring mass systems, that is needed in order for our system, for the mass system not to oscillate out of control and break our spring or our dash pump. Okay? In terms of second order linear homogeneous equations, this comes from the case 1 situation here. Okay? And I'm saying that because this corresponds to a response that looks like this. And again, when I write these cases here, this case actually comes from the theory behind solving these kinds of equations. In actuality, this example here is a case 4. Okay, so I'm going to erase this so that I don't cause any confusion here. So in terms of spring mass systems, this is a case 4. But when we figure out, well, what's the response going to be based upon what the roots look like, it is case 3 from that body of knowledge of solving second order linear homogeneous equations where all of the constants or all the coefficients are constants. All right, so again, because of the fact that this response here has exponentially decreasing functions on it, we know that the response over time is just going to act like this. It's going to eventually get the mass back to equilibrium. If we label this Y, label this T. So that's what we expect. Now, next example gets into how we name our 4 cases. And so we wanted to decide what the expected behavior of our response of our spring mass system should be based upon the different dampening coefficients that we just talked about. So what I'll do is just start here with the case where we had no dampening once at all. And so here we know no dampening goes along with the dampening constant being 0. So we know that this would be that choice. And that means that our system will oscillate without end from t equals 0 on to infinity. For the case where we use fluid A, that was a response to where we saw that we did have some dampening, but it wasn't fast enough, okay? And so that was our underdamped situation, and that is exactly what this particular choice is here. We said that fluid B was our case where we had a critically damped situation. So that would be this choice here. And again, the system will try to oscillate, but it won't complete a full cycle of oscillation. because we know as t approaches infinity, the system responds in a more exponential fashion. And remember that critically damped is the borderline in between our spring mass system responding like a sine or cosine function to responding exponential. And of course, that leaves the last choice where the dampening coefficient was 26, and that's the case where we're overdamped. And again, system will never oscillate in that case. So the material or the fluid that is in the dash pod is so thick to where any type of force that's applied is just not going to allow it to oscillate before it kind of settles out and goes, the mass goes back to equilibrium. Okay. It will get to equilibrium, but it'll get there much, much slower than it would otherwise. All right. So the next thing that we're going to do is see, well, what are our graphs going to look like for each of these situations? And so what I'm going to do is, instead of trying to draw these graphs here, I'm going to show you what they look like in Desmos, and I'm going to keep up with what the various response functions y of t were, so that you can kind of see the difference in between them. Okay, so I have Desmos pulled up here, and what I've done is I went in and I've typed in all our responses. So we're looking at the spring mass system where our force function here is 0. Our dampening coefficient, we start off being 0. And of course, a response of this just basically looks like cosine of t plus sine of t. And of course, that's what it looks like. Okay. Now, of course, with this, the system will oscillate forever and ever and ever. We're not going to have any dampening. So that means that the mass technically will not go back to equilibrium at any time. Now, if we apply the dampening to dampening of 18 for the dampening coefficient, if we apply that, then of course our response is this. And if I apply that, do you see how that acts differently here? Okay. Now, again, like I mentioned in the first video, that because of the low numbers that I use to make the math relatively easy, this is not really doing exactly what you would imagine. We would have a few more oscillations here before it would actually die out. And I'll show you what that would actually look like here later on, if we had something that was a little bit more realistic like that. But again, the point is that you see this little hump that's right here. What it's trying to do is oscillate. Okay. Now let's turn off the case 1, leave on the case 2. In the case where we have critically damped situation, you see here how this doesn't even have like a real big hump in it. It just kind of smooths on out, and it's going to approach the position is going to approach equilibrium, which is y equals 0, as fast as it possibly can. And if you see here, it looks like it's going faster here, but what it's trying to do is oscillate, and it just sort of catches itself and it says, nope, I can't do it. Okay. Whereas here, it's trying to oscillate as well, but as soon as it starts off, it's like, ugh, can't do it. And so that's why it starts off a little bit higher than this one. Okay. So let's cut this off and now put on the case 4, which is we're overdamped. And so now in the overdamped case, you see how it acts purely exponential at this point. It's not even trying to act like a sine or cosine function. Everything just decreases exponentially. And so this is what these 4 different graphs would look like if we were to have them all there together. Of course, again, we start off with this one, and then we have a little bit more dampening, Then we have more dampening than that. And then the maximum amount of dampening that we applied to our system, we see what that looks like. So now what I want to do is show you what would our graphs look like if our numbers were a little bit bigger. And again, I just threw some numbers in to kind of make the graphs look more like what they would realistically look like if we were, modeling some real life situations here. So we see that I've basically increased the frequency by a factor of 4 for the case 1 situation where we have no dampening. So that means that our period is 4 times smaller than what it was, which means it oscillates 4 times as much within the same amount of time. Okay. So if we go to the case 1 where we have some dampening, you see how the blue function, it oscillates some, but eventually it dies out. And so in actuality, that is how most of these functions, when you model a situation via a spring mass system, that's how it's going to look. So the red function is what it looks like when there's no dampening occurring. Blue function looks like what it is when we have some dampening, but not enough to make the oscillations die out quickly. So if we look at the case where we're critically damped, then we see here that tries to oscillate, but then it catches itself and it says, all right, I need to act like an exponential function now. And it just does that and basically fizzles on out to 0. Okay. And of course, this last function here, and I'll cut this one off. This is the one where, again, it acts purely exponential here. And notice that starts up high up here at x equals 0, or t equals 0 rather, and it just decreases exponentially. Okay. Whereas for this one, it's trying to oscillate, but then it realizes, nope, I need to act like an exponential at right about this point, and it starts to come back down. And so this is what it looks like graphically whenever we have a spring mass system with its homogeneous or transient response only being considered, meaning that we do not have an external force being applied on the system, and we see what the various responses look like. Of course, I'll go back and put all these up again. So we see there's a lot of oscillation here, no decaying. Then we see there's some oscillation here for the blue graph, but decaying. And then for the green graph, which is the critically damped case, we see that it's really trying to oscillate some, but it just can't make a full cycle. And then of course, the purple one is like, nope, I'm not even going to try to act like I'm an oscillatory type function. I'm just going to act straight exponential at that point. And what's essentially going on here, and I'm just going to use my cursor to try to model what's happening. In the case 1 situation, you got the mass going back and forth like this. Okay. In the case 2 situation, it starts to slow up and do like this. In the case 3 situation, it will start off that way and then just come back like this. And in the case 4 situation, when it goes like this, it'll just kind of do like this back to equilibrium. Okay. So again, you have case 1 where it's just going back and forth, back and forth, back and forth. Case 2, it will go back and forth, but eventually die back to equilibrium. Case 3, it won't be doing all this oscillating here. It'll just kind of and then come back. And then case 4, it'll go and then just slowly get back to equilibrium that way. Okay. So I hope this video helps in having you understand what our transient or impulse response for our spring mass systems look like. In the next video, which is going to be the final one, what we're going to look at is what happens when we apply a force function onto our system. And we're going to look at the case when our force function is constant as well as when our force function is not constant, and see the difference in that.